recommending the gear that's best for you. I think a lot of people know us for our support. Instead of calling a vendor to diagnose one little piece of the air chain or their facilities, Heartland can really look into the whole picture and see where any issues might be. There is some news. We just purchased a company called Pedestra that is a tower cam management system. It's very streamlined. This is very new, so I don't have much of a elevator pitch for it, but you can up to 8 outputs and really nice UI, and it's much more affordable than the other options out there. So if you have interest in that, let us know, or anything else, please let us know. I really should have my email up here, but it's just my last name, Hudgens, at hvs-inc.com. And with that, I'm happy to give it away to Jared, who is the important part of this and really knows it all. So Jared, I'll leave it to you.
Hey guys, before we get started, I totally forgot to ask Bill Sewell to ask you all, is it okay to record this to have on our YouTube channel?
Okay with me. How about you, Jared?
Yeah, it doesn't bother me. Just so you know, like this is I'm not a good public speaker, so this isn't going to be probably nearly as formal as a normal, like a typical presentation would be. But yeah, I mean, if you're okay with the corny nature of it and my stumbling around trying to find the right words, by all means.
Perfectly fine. Thank you.
Okay. Yep.
Jared, you're hard on yourself.
Gotta be. Okay. So yeah, we'll jump in here. Hopefully cool. Everybody can see this okay? Just making sure.
I think I'm still sharing.
You're at the point where it says starting out, right, Jared?
That's correct. Yes.
Yeah, we got it.
Cool. All right. So the intent behind this is more or less what I've done to train folks here at Heartland as they start out. So, I think it's pretty common around the industry that, broadcast engineers are not, real real frequent in happening. So, we at Heartland we've kind of started the philosophy of, you just got to pick people up who are interested and try to train them from the ground up. So I apologize if this is, very, very low level for some of you folks who have been in the industry for a while, but this is kind of our attempt at Heartland as to how to get new people brought up to speed. So kind of the philosophy here is there's a lot to learn in broadcast. Obviously, there's probably many of us who have been in the industry for double digits at this point, and you still learn things, right? And it keeps changing, so it's a constant learning session. So what I tell our folks is it's not essential to know everything immediately, right? You can get the basics down, and then you can grow from there. And then the more that you know, the more you know that you don't know. So, as you start digging into some of the standards that we deal with, you'll find out that there's, a whole lot to it that you may not have known. You understood the basics of it, but like I said, it's kind of a learning thing as you go. So I like to kind of equate it to driving a car, right? So a lot of us can probably drive the car, but maybe don't understand how the engine works. It's the same thing with broadcast. At least for what we do at Heartland is, when we start bringing in new folks, we try to teach them like, all right, this is how you drive, right? Gas pedal, steering wheel, blinkers, so on and so forth. And then how the engine works comes later. So that's kind of the philosophy. By all means, I'll try to do my best to stop for questions as we go here. If you do have something, and feel free to correct me if I say something wrong. I'm not gonna lie. Like, there's a lot of stuff here, and I I may get things wrong from time to time, but feel free to ask questions or let me know if there's a different reason for something that I may not have hit on right. So, all right, so this first slate here, I'm actually going to ask Bill Sewell to help. He had asked that I put this in, so I'm going to let him speak to this a little bit, Bill, if that's all right with you.
No, absolutely. I think, and part of, why I'd asked Jared to come up with this class was, again, we are running through so many new engineers that we're trying to train up, and it's kind of helpful to talk about how we got to here, right? That the DTV 8VSB standard ATSC 1 has been, on the air for more than 20 years, and the only way to get what you want, get your locals for what, 15 now, more than 15 years. So I think it was worth showing out that, what you're basically doing is trying to use the same 6 meg channels we'd had since the dawn of time and figure out how to make a digital modulation scheme and shove 19 megabits of data into that chunk. So, we're just showing the WTKR contour as a basis, and on the lower left, which I think everybody on this call is good with, the difference between the old analog carriers and what the 8VSB signal looks like. So with the 8VSB signal, right, we're somehow getting 19.39 megabits out of a 6 meg channel. And then obviously the encoders are where we're going to turn all that data into, instead of just a line of ones and zeros, something that's actually useful to decode.
Yeah, I'll say the graphic on the right there for robustness and how far the signal can travel is from rabbitears.info. I don't know if all you guys are familiar, but it's a very handy site that we use here at Heartland quite often. A lot of good information there, so kudos to those folks who keep that up and running. Okay, so more or less when we have folks start out, we try to teach them that this is the data stream is kind of hard to understand, I guess, if you're not used to it. But what I like to equate it to is how plumbing works for the most part. So most folks understand how water travels through a pipe. So that's kind of the idea behind this, right? Is data bits going through a cable is very similar to how water gets to all your appliances in your house. And by nature of this, we can have a pipe that goes from A to B or from A to multiple places. So just trying to get them to understand like how data moves through a system is the first step. So this is the way that I like to go about doing that for folks. So the size of the pipe is the other thing we like to talk about. Even though the cable size doesn't change, the amount of data that we can put through said cable can change based on, what we're attempting to do. So, we always say there's always the question of, how much can we send? And it's like, well, how big is your throughput or your pipe, if you will? And is it a small pipe like 10 meg, or is it a big pipe like 100 meg, something like that, right? So that's the other thing we try to instill to the new folks here, is that you can have a bunch of different variations in how much data you can put through one of these pipes, even though um, you know you don't see the cable size change basically. So in coding, obviously this is kind of, our bread and butter. So, we want to make sure that this gets hit home pretty well for our people. And the way that I like to describe it to them is it's basically like taking a puzzle. Don't think about this too hard if you understand this very well. This is a very simplistic means of getting the point across. But basically, think of like how a puzzle is manufactured, right? The whole thing's laid out, and then it's cut up into bits, put in a box, and then it travels to wherever it needs to go, right? So that's the idea behind encoding, is to take something that's a whole picture, and squish it down into something that's easily transportable, and then on the other side to bring it back up. The reason we do this is that it's easier to transport, the smaller bit rates or the smaller package than it is the giant package that, is initially made by the content providers. So then Same idea on the opposite side of decoding is how do we get the picture back to the way that it was initially, right? So decoding is basically just the opposite. It takes that crunched up package, expands it back out so that we can see the full image again. Same idea here. It's basically reassembling the puzzle at the other end. Just happens way faster than, you know, like if I were to do a puzzle, sit on my kitchen table for like a year. So the way that we make that work is with PIDs or packet identifiers, right? So these are like the labels and the building instructions for how to get these components back in line so that a consumer device can then look at them, right? So I think everybody's probably familiar with how PIDs work here. You know, there's other things that go into play here, things like metadata and so on and so forth, which you know, we can talk about a little later. So the components, um, every stream that we want to be decodable needs to have specific things, right? The nuts and the bolts of it that kind of hold it all together. So the PAT, the PMT, PCR, and then your components, your video and your audio components, and then PSIP tables. Uh, there's other things obviously that can sit in here, data packets. You know, even sometimes if I remember right back some time ago, we used to have like IFP feeds that could run through here. But you know, that's not something that I see a whole lot of anymore. But these would be the components that make up the stream, and they're quite important to the whole broadcast chain. So the way that I like to think of the component structure is how they reference each other. So for instance, the PAT encompasses the PMTs, which encompasses the uh, stream components, the audio, the video, and the PCR. So in a way, it's kind of like a Windows folder structure, right? So if you click on the path, then you get the PMTs, and then the PMTs then reference to the other components. So on the right there, you can kind of see how that works or how I think about it in terms of a Windows structure. On the left there, you can kind of see how it would work in like a hierarchy. Though Pat, you know, would be the CEO, which tells the managers what to do, which tells the foreman what to do, workers what to do. That's kind of how this structure works. If you're missing one of them, the rest of them don't exist, more or less. So we'll jump into video components. So today, for ATSC 1, we're using 1080i, 720p, or 480i, or 525 in some circumstances. So that's notated up here on the upper right as to what those raster sizes look like. We can also have closed captions, which are the words that go across the screen to show what the readout is or the transcript is of the audio. AFD, which is changing the format based on codes. So if you had a 16:9 or a 4:3 and your content would switch between the two, you would use AFD to switch between those without having to manually change anything. And then the VANC data, which some of this is, you know, already held within that closed caption, and AFD is held within the VANC, but there could be other things like SCSI triggers and things of that nature. We also can do up-down cross converting, so meaning taking like a 1080 and then down converting to a 480 or vice versa, a 480 to a 1080 or 720. In a lot of the pieces of gear that we're going to deal with, cross converting is HD to HD. So 1080i to 720p in our world is mostly considered a cross convert, not a down convert. That one catches some folks. The different type of codecs. So for ATSC 1, we're mostly talking MPEG-2. I've seen one station roll out MPEG-4. I think it's not common though. I think most folks have found that MPEG-4 is not decodable by a giant portion of their viewer base. So unfortunately, you know, I don't know if we'll ever get to a point where MPEG-4 is real prevalent. But it is used pretty highly for transferring signals from, one station to another station in the case of an ATSC 3 channel share, or from, one location from a station to another location in that same station group. And then MPEG-5 or HEVC is now the common codec being used for ATSC 3. In Brazil, though, they've started rolling out VVC already, which is the next one. So we'll have that to look forward to, I'm sure. But as of right now, everything done here in the States is using HEVC. Something big that I won't have to touch on too much here, but for our new folks, just understanding the compressed and uncompressed realm, which signals go into which end of the equipment, right? So uncompressed being the SDI, compressed being the ASI. Generally speaking, there's other things, IP and all that we can talk about, but for the most part, in an encoding chain or an air chain, we'll go with these two. So the goal is to get from SDI to ASI by the end of the chain so that we can send a compressed package out to the consumer so that they can decode it on their end and look at it on their TV. So a lot of the questions that we'll get when we talk about video with our newer folks are the why do you do interlaced versus progressive? And the reasons here are generally because of raster size and efficiency in the encoding systems at the time that they were made. I would imagine that most of the time now we could probably do 1080p, but with the way the standard was set back then, it was easier to do 1080i instead of 1080p and so on and so forth. So as to why we don't do 480p, I guess I'm not entirely sure. I want to say that somebody told me this at one point, but I don't recall off the top of my head. Bill, actually, I think it might have been someone from your team who had elaborated on this the last time.
In the analog world, in the way back world, I think somebody came up with interlacing because literally the electron guns and the old tubes weren't fast enough, you get flicker. I mean, I'm talking the 1940s or 50s. So I think that's how the original NTSC standard became interlaced. And then really everything, in the DTV, anything we do that's standard def is just because it's old and we're pulling it in that way.
Hey, I can give some clarity on that, and I can't explain it to the greatest depth, but there's a great SBE workshop 2 summers ago where it was explained that it was all about the progressive in Europe is based on the 50 hertz reference versus our 60 hertz. And in the United States, they wanted to be backward compatible. And it just turns out that the math we're getting this signal through works out perfectly at 50 hertz. So I'll leave it at that, but you can look, I will provide a link to everyone if they make that video available. It was a great SBENS workshop from Washington, D.C.
Fantastic.
Yeah, thanks. I appreciate it. I'd like to learn too, because I always kind of, I'm always like, I can't tell you for sure. So if I could learn it, that'd be great. So PCR or program clock reference, the way that I like to explain this to our folks is, this is a timestamp, and it's very important. When the PCR is off, things can get kind of dicey in a hurry, right? So the graphics here are more or less to show, like Usain Bolt down there in the left is generally what we don't want to see, right? We don't want to see items showing up with one way out in front of the other, or not showing up or showing up behind, because that's when you start to run into problems with your stream. We really want this to kind of everything to line up and almost be like a tie at the other end. Some of you may be familiar with like the newer encoders having complaints from specific satellite providers where they say that the PCR and the PTS and all that are coming in at different times and it causes problems and things like that. And yeah, it's fairly prevalent with the newer encoders. It doesn't seem to affect the stream a whole lot, but that's one of the conundrums here, right? Is that if the PCR and these other timestamps are off, they'll throw an analyzer into a tizzy. Sometimes you can get your audio a little delayed or your captions delayed and things like that. And that's what, this is meant to do, is it's meant to timestamp things so that everything stays in line and can be decoded and put together correctly. So the audio component, I apologize, this gets a little bit hard to explain, I guess, especially for newer folks. I feel like the audio component is generally the harder of the two. For us, even, even though the video component probably has way more processing that it needs to happen to it within the encoder, for us and what we do setting up encoders, it's generally the easier. You set it to a format and then you assign it to a stat mux or a specific bit rate, give it a codec, and away it goes. The audio has a lot of different handles to it, things that we don't have to do with video, things like processing and different buses to pull from and down mixing and up mixing and things like that. So it's a little more hectic. So basically, when I start explaining this to our folks, it's like a 3-day conversation. So I apologize. We're gonna sandwich it pretty hard here, but same as what we have with video, we have our uncompressed or compressed. So PCM generally in our world is our uncompressed audio. AC3 and AC4 would be our compressed. AC3 typically for our ATSC 1, AC4 for our ATSC 3. You could even run into the AAC, that is sometimes used along with MPEG-4 to send video across links and so on and so forth. A lot of the times we'll see stereo, and recently with dot ones or your HD signals, we'll see 5.1s. Now with ATSC3, we're starting to get into even higher numbers than that. I think it's like, I can't remember, 5 dot or 7.1.2 or something like that. I'd have to go back and look, but that's your different audio channel or your different left, right, center, low frequency. We'll talk about that in a little bit. A lot of the times in how we discuss audio here is we'll call a main channel or a SAP channel. A lot of times SAP gets confused with Spanish. That's not really the case if we want to get into technicalities, right? That's just a secondary audio program. So it could be anything, could be French, could be descriptive, so it gets a little bit of a incorrect name, I guess, when some folks talk about it, but it's just any secondary audio that comes along, and then you can have tertiary and all that kind of stuff in some cases. Embedded and discrete. So this is the depiction below where we have video and audio running on the same cable. That would be embedded. Discrete would be video and audio on separate cables. Today, embedded is pretty heavy. We don't see a lot of discrete anymore. Going through our encoding chains, it's almost all embedded. It makes life a little bit easier, in my opinion. There's way less cabling and things of that nature. A lot of gear nowadays that looks at audio can take it in an embedded form and split it in the unit to look at it. So that's also helpful. And as mentioned before, audio processing, this is where a lot of the difficulty comes in for audio. And I think in the following slides here, we'll talk about how some of these things are done. So column processing, I'm sure we're all old enough to know that, program content and commercials wouldn't always be the same volume, right? So commercials would blow you out of your chair half the time. So calm processing was introduced here. I think it was via legislation that tells you have to have your audio within a certain range over a certain amount of time. So the picture in the upper right here kind of shows how that works, right? Your dial norm, or the line here that's straight, is where you want to be, and then plus or minus 2 dB is where you want to stay. So it yeah, obviously the white line here probably showing the audio as it is in decibels can drop to basically nothing if you're going from one piece of content to another. So understandably it's not going to keep it in line the whole time, but the goal is to get it back up and close to that line as possible over time. Lots of pieces of gear can do this now. Anything from your typical audio processors that you would see, the linear acoustics, the cobalts, but they're even starting to put this into encoders at the moment. So, the harmonics and the ATEMs are looking at doing this kind of thing right in the encoding platform to kind of gain more on the air chain. Something else that we've done quite a bit of is SAP replacement, or priority for SAP, or descriptive, down mixing, so presence detection and things like that. So basically what this is if like we'll talk about SAP down mixing first. So something we can do is, if there is no secondary channel, but the station wants there to be a secondary channel there 100% of the time, we can take a down mix, either 100% of the time or part of the time, to make sure that there's always audio content there. Not that some programs have it, some don't. Grandma at home hits the SAP button and half the time doesn't have audio. So this is a means to make sure that there's always something there. So other things we can do is priority 7/8. So I don't know if it's still real common today, but they would, there were times where you could send a SAP on 7 and a descriptive on 8, and we could set up specific pieces of gear that could presence detect, see if there's actually audio there, and then do some audio routing in order to make that mono channel a stereo. So that's something else that we would do, and that some folks prioritize descriptive over SAP or vice versa. So that would be the reason behind that. So audio routing, this is where things get a little off the rails, especially when you get into more complicated designs of this. So the way that I like to explain this to our folks is, think of, like a big highway, right? You have all these lanes. Those are like the buses within the card that you're trying to put your audio on. So, each audio channel, left, right, center, whatever, has its own lane that it would ride along on. And
like from like Douglasville area.
okay, I'm assuming that wasn't a part of the meeting. But sorry, kind of sidetracked there. Anyways, the lanes are meant to keep your audio channels distinct, and then as you move them through the card, you can pick them and choose them, and figure out what you want to do with each individual channel. So on the bottom left is basically a depiction of what an audio processor card looks like as far as modules for Cobalt 9934. So you can see there's a lot of different ways that you can put audio through here, and that's all based on putting specific audio channels onto these buses to send them from one location to the other, right? So that's kind of like how this little goofy depiction down here about, if you wanted to take and send your audio to the gas station or Walmart and then get back on the highway to go out the back of the car, that would be like taking your audio and then going through this audio processor. Now they have these processes kind of jumbled together here, but each one is a specific function within that you could send the audio through or not send the audio through and still come out the other side having processed audio. So that's kind of the idea, is lots of different ways to get through here, but the way that the audio moves is very similar to roadways and stores, more or less. So ancillary data, we kind of touched on this before. You got the Hank and the Vank. I don't think that Hank gets used a lot anymore. I could be wrong on this, but I I can't think of a single example of this in the recent past that I've had to use a Hank. But Vank is basically the little section above the raster that sometimes you'll see on TVs and sometimes you won't, depending on what format gets picked. But the best example I can put of this is sometimes in the upper left you'll see little white dots kind of flickering, and that's generally caption data. Most of the time you see it on an SD because the raster will get picked for 720 by 480 instead of 704 by 480. So you get to see those extra lines up there, and you can see the caption data flickering as it comes through. But as mentioned, you can get AFD. So the upper right there kind of shows the difference in AFD and how that functions. If you're sending different codes down and how that would treat on a raster. And then the bottom left here is talking about how SCSI can be used. So to run ads and breaks, we've seen it to do logos and things of that nature as well. But that's just a little piece of data that rides along in the stream that can trigger, very similar to how GPIs work. Without having to actually have those physical connections. And then the bottom right over here is going over captions. Now we really don't do 608 captions anymore. Everything gets translated from an encoding standpoint. So that would be the black background captions that you see today. PIDs. So this is more or less going over the scheme and how we've set it up here so that our folks can learn the pattern, if you will. So paradigm scheme is what it's called, and you can see the two different types here, the decimal and the hexadecimal, and this is how we would assign PIDs to different components in the stream so that we can identify them later. One of the questions that we get asked most often is, well, why don't you just start with one? And I took the time to go and find the table over here that kind of explains what the rules are as to how these are used. We cheat a little bit here at Heartland. When people ask me specifically about this, I just tell them, well, 1 through 47 are used for emergency purposes. Don't use them. And that's usually good enough for folks to kind of stay away from them. But if you wanted the actual descriptions of what they are, that's them right there. A lot of the times nowadays we're seeing these mixed and matched, decimal and hexadecimal. I mean, it really depends on the piece of equipment as to which one you're going to see. So there's no guarantees as to which number you're going to have to be put into, but it's generally pretty easy to tell which ones are which by the 0x in front. That's usually an indication of hexadecimal. Now, sometimes, and maybe the stations that you guys work at, you can identify this, but the PID schemes are really, I don't want to say arbitrary, but maybe open for interpretation. You don't have to follow this scheme. You could put in all sorts of different PID numbers, I guess, to assign stuff. and your stream will still work. So this isn't like a hard set rule. It can make it a little bit difficult with newer folks though, who don't quite grasp that, right? Is there a guideline, not necessarily a rule. It's nice when they're all in line. Makes it a lot easier for people to decipher. But you know, you could have these things switched around, and your stream would be fine. It's more of, you know, telling the decoder um, where to go find these things in order to make it work. So even though it's set up this way, it doesn't mean that it's always followed this way. Same thing with program numbers. More or less, we assign a program number to each. So again, pulling this from rabbit ears so that you guys can, you know, see what that website all has to offer. It's very helpful for us here at Heartland when we have to get in and start setting up encoders. Makes data gathering a little bit easier. But here you can see that there's the physical channel column here. This shows the actual program number. So this is the RF channel that gets sent out, and then this .3 is actually the program number that's assigned in either the mux or the encoder, whatever, you know, wherever you're setting that. So oftentimes we'll get questions about, you know, well, what happens if my PSIP fails? You know, what happens to my stream? And if your PSIP goes away, like your TVCT, what you'll see is you'll actually see this physical channel show up on air, right? So instead of being 5.1, your stream will show up as 22.3. So if you ever see that on air, that's a good indication that your PSIP is gone. Some folks get really lucky with this and their display channel and their physical channel match. That's pretty much not, you know, not always the case. So then we get questions from folks about, you know, well, why do you have a physical channel, virtual channel? And I think this came in before my time at Heartland, but it was due to the digital transition, I believe, right?
Yeah, I mean, basically, if I'd been channel 3 since the dawn of time, it'd be a little hard, you know, in the analog days, it was a little hard to say, oh, well, now we'll be channel 40 and we'll just have to rebrand everything. So I think that was the underlying business reason to be able to mask that.
Yeah. Yep. So we,
None of
you
it
know,
seems to matter anymore. Now I go on YouTube TV, it just says WTKR. So
I'm pretty sure that's all done via multicast address. Um, but yeah, so we, you know, we always have to explain here, you know, that the physical channel and then what's assigned, or the RF channel and then what's assigned in PSIP, you know, are different, and knowing the difference between these is good. You know, this is what's coming off the transmitter. This is what's being said in your PSIP. Again, with program numbers, they go out of order. So sometimes, you know, so here's one that we had in Green Bay, where you know, the program number starts with 3, which is typically what we'd like to see if we follow paradigm scheme. You'll notice that there's a 14-2 in here, which sometimes is a head scratcher for folks, but that's a channel share. So that's part of the ATSC 3 lighthouse, right? They're shipping over SDs to other channels and putting them on. So even though this is a different channel number, it's riding on this transmitter due to the ATSC 3 lighthouse. Sorry, I got to move my Zoom thing here. But over here, you can see that this one doesn't necessarily follow paradigm because the program number starts at 1 instead of 3, but it goes, you know, in order after that. Still okay, it works, it just doesn't follow the scheme. And then you'll have another set here where you can actually see that the program numbers go in order, but the major minor doesn't go in order. So this is one of those things, you know, where it's good to understand that even though, you know, it's a guideline, it doesn't always get followed 100% to spec. So hard to get newer folks to see that and be like, that's wrong. It's not necessarily wrong. It's just, you know, a little out of the ordinary. So PSIP, the best way that I can describe this to our newer folks is that it's the information that you get when you hit the info button, right? That's the quick and dirty. There's quite a bit more to it, but that's the best understanding that I have seen from newer folks. So typically we'll split these into the upper and the lower. So upper being the PSI tables or the PAT, the PMT tables, and the lowers being the MGT, TVCT, RRT, EIT, ETT, and STT, right? Those are the ones that are listed down here. So this is more of a slide on lower tables and what those do. So master guide table kind of pulls the rest of these together. It's kind of how the PAT works with the PMTs, right? The PAT holds all the PMTs, the MGT here holds everything else. And it's equated to PID 8187. So if you're ever looking in an analyzer and you see that, that's your PSIP tables being generated. So to go over these a little bit, TVCT is what creates your major, minor, and your short channel name, right? So in the top depiction there, you can see WWCWDT. That's a short channel name. And that comes from your TVCT, also the major, minor. So like, for instance, if you had 7.1, right, that's generated in your TVCT. Rating region table, this is basically what it sounds like. This is the rating structure for the US, PG, PG-13, all that kind of thing. EITs and ETTs, this is the show title and description, so the short synopsis. So down on the bottom picture there, Big Bang Theory would be EIT, and then the synopsis underneath would be your ETT. Typically, these are brought in from a third party. If you guys are familiar, Titan TV, generally a pretty big one. And then you'll have some others as well, ProTrack, Myers ProTrack, and whatnot. And then the STT, the system timetable, this is what makes sure that your guides are showing up at the correct time, according to where you're at in the US. So repetitions, I like to give this its own category because a lot of the times, when we're talking about bit rate and specific. But there's another measuring unit here for things like the PAT, the PMT, PCR, and PSIP tables, which is how often they appear in the stream. So I equate them to monkey bars because when you're trying to get across the monkey bars, you need that next monkey bar to be close enough to you that you can grab onto it without being stuck, right? So all of these components of the stream have specific repetition rates. I think I list them in the next slide. But something that we'll do here at Heartland, just as a general standpoint for setting things up, is we'll adjust these repetitions a little bit in order to make analyzers happy. Nobody likes an analyzer that's showing yellow and red. So what we'll do is we'll decrease these repetitions a little bit to make sure that the analyzers are happy. And the good news is that the little amount of data that you sacrifice for pushing these tables slightly sooner than they're supposed to is that it really doesn't affect the stream, but it sure does keep chief engineers happy when their analyzers are showing up as green. Oh, maybe I didn't put in the repetition rates. Sorry, I thought I did. Anyways, PAT comes out at 100 milliseconds, PMT at 400 milliseconds. PCR, actually, it's that one, it comes out at a 27 megahertz. So I believe that in the past, this was done by an oscillator in most units, and nowadays they've kind of done away with it because they've gotten COTS, or consumer over the shelf PCs, and now they wrote in a way to do this based on processing rates. So the processor actually becomes your oscillator, and we've noticed a little uptick in jitter in some situations due to this. I don't think it's as precise as what the old oscillators were, but so oftentimes what you'll see in newer encoders or anything that's doing processing, is if we have to insert a PCR, we'll actually do the same with what we did with a PAD and a PMT, is we'll actually increase the amount of PCRs that are sent, just due to the jitter that we're seeing. It just makes sure that we give ourselves a little bit of a buffer there so that we don't have PCR problems. PSIP, I don't remember all of them, but you're getting closer to half a second and a second once you start getting into some of those. So we don't really mess with them too much. The real important ones are PAT and PMT. If you start losing those, you'll start losing your stream. So we want to make sure we get those right. Okay, so bit rates. The major one in ATSC 1 is the complete pipe size, right? 19392658. We have to kind of drill that number into the new folks' head because it shows up in just about every single encoding system that we mess with for OTA. There's two types of bit rates that we'll typically deal in: constant bit rate and variable bit rate. So constant meaning that it, you set it and it stays there. Variable bit rate meaning that it can kind of bounce around. StatMux is a very good example of a variable bit rate. So we'll talk about that in a little bit. But why you would choose one over the other? So obviously with your OTA transmission, right, constant bit rate, we need it to stay at 1939. It can be below that, but it can't be above it. So we don't want it fluctuating up and above, right? So we want that to be consistent. Same thing as if you have a fixed pipe that you're trying to send a bit rate across. If 10 megs, we don't want the video to try to pull 11, right? Well, we'd have a problem. So constant bit rate for those kind of applications is generally good. And variable, we'll talk about. We can do variable bit rate within a constant bit rate, which is kind of what StatMux is. So talk about that in a bit. No, or no. So StatMux basically gives the encoder the ability to look at what resources it has available and what the videos are doing that it needs to encode, and it doles out the resources based on that, right? So the goal is to hit a specific video quality, and it'll try to allocate the resources to get to that point. So there's a little difference in how vendors treat StatMux. Some include everything from null packets to audios to PSIP, and some want you to pull, the nulls, the PSIP, and the audios out and just focus on the video. So this isn't an exact. I'll show you the way that we typically have these set up on the encoding systems that we sell the most of. But just understand that some vendors may do this differently. So as mentioned just a minute ago, typically when we run into StatMuxes, it's based on video only. So you want to subtract everything else out of that 1939 so that you can effectively set your video to pull the right amount. If you have your StatMux pool too high, you run the risk of overrating, and then your stream starts to fall apart as chunks of it are lost due to the overrate. So one thing we can do in StatMuxes is we can set minimum maximum bit rates, right? So this is as low as your video will go or as high as your video will go. And there's lots of different variations to this, right? You have HD versus SD. Some of you guys will have, 2 major affiliates. You'll have a contract in place that means that you have to have a certain amount for one versus the other. So it gets a little bit hard to explain, what there's no good one set standard for how StatMuxes get set. Usually it's good philosophy that if you don't have some kind of contract in place that you have to meet, that you leave this really open, because the encoder is going to do a bunch of calculations, which we'll talk about in a bit, that can say whether or not a video needs a specific amount of data or not. So for instance, right, if you have a talk show on, your HD may pull less than your SDs at times, depending on how you have your StatMux set up, because your SD could be gritty old video that the encoder doesn't know it it shouldn't try to encode the blips and all of that, the fuzz in the picture. Um, so it looks a little goofy on a um, bitrate analyzer because your SD is, you know, pulling way more resources than your HD. But that's kind of kind of one of the goofy things you'll see. So you kind of got to understand what your content is in order to make sure you get this set correctly. And that's why a lot of the times when Heartland sets up StatMuxes, the SDs get capped pretty low, just for that particular reason. The other thing that we'll run into here is priorities. So I think you guys are probably used to this, but very high, high, medium, low, very low. That's basically the judge. When the encoder needs to pull resources and two services want it, obviously the priority comes into play. Now there's some other things that are coming up in encoders nowadays, like targeted average and things like that, that sometimes if you have a license for it, you can do that, which is another layer. Regional stat muxing and all that, where you can have a stat mux within a stat mux, but that's getting kind of way out in the weeds. You don't see it a whole lot for just the OTA streams here. So the calculation that the encoder runs for the stat muxing is called part of it is called group of pictures. So the way that you set this up is basically telling the encoder to go and look ahead and behind and see what's changed in the picture or the frames that it needs to encode, right? So if you got a talking head and there's something in the background that isn't moving, the encoder is not going to re-encode that. It's going to, kind of push it through with very little bit rate assigned to it so that it can use the bit rate on things that are more heavy as far as changes in the screen, right? So this is an interesting way of doing it. I don't want to get too far into all of it because it's a lot and complicated, but basically the way that I like to try to explain this for newer folks is that it's like telephone, right? um the longer some of these go, sometimes the worse the quality can be, right? Because you're looking at an initial picture and then you're trying to make adjustments based on everything that's coming after. So eventually, right, you want to have another clean picture to start. That's your iframe. Um, some codecs do better with longer GOP structures and some don't. That's really based on the codec. So you kind of have to look at, which codec you're using to figure out which gap structure you should be using. And the other thing that I like to talk about is quality versus efficiency. So, if you have a bunch of iframes in a row, it's going to be very good quality, but it'll be rough on efficiency, right? So some encoders that aren't on a giant server, right, can kind of struggle with this because they're not meant to be doing iframes every single time, right? So you kind of give it a bidirectional and predictive to kind of lessen the load, right? It gets more efficient, but it's going to be less quality in the long run. So that's kind of how we go about describing how to choose this. Now, we try to find a best practice for the encoder that we're working with, and we'll start there, right? But when it comes to figuring out your specific needs for your content, then we'll have to dive into it a little bit more and see what are you aiming at, and how do we get to that point. So typically in a stat mux, you know, we'll see all different sorts of things, right? I mean, we'll have stations that have 2 HD, 4 SD. We'll have a station that has 16 SDs in it. You know, it's kind of all over the board. It really depends on what the station is doing. But more or less, this is what we would see as far as a general layout. So the pictures that you see on the bottom here from a Triveni stream scope, but this is local to us here, Milwaukee WTMJ. You can see that the yellow service here is the HD, and you can see how much of the pie of that 1939 that your HD takes versus what the SDs are taking. So you can kind of see what that looks like. This other one here is just a different look at the bit rate. It just shows the kind of ebb and flow over time, and you can kind of see where specific services are pulling specific bit rates. Okay, sorry, that was a lot of me talking. I guess, are there any questions?
You know, I see a question in the chat from Elliot about is there a good resource where you can read up on stat muxing?
Yeah, I would imagine that, you know, if you go to some of the actual encoder manufacturers, that you could probably find some stuff. I mean, if you're looking for a deep dive on stat muxing, you know, I'd be more than happy to you know, have a side chat about it. You know, we can go over what it looks like in an encoding system and all of that. You know, there's a lot of variance to it, you know. So if you have specific examples of what you're looking for, I'd be more than happy to sit in with you and go over what that looks like. But otherwise, yeah, I mean, I would aim at the vendors. You know, they might have some good information on it. Or I can try to find a link and pass it on one way or the other, you know.
And then good acronym question from
Uh-oh.
Chris Williams. What's PSIP actually stand for?
Oh boy.
Right, it's like Program System Information Protocol or something like that.
Yeah.
Hold on, let's see if I'm probably halfway there.
That's
And no,
it.
you got it.
You got
Is that
it.
it?
Yeah,
Yeah, it's
program
program
and system
and system information.
Okay.
Yeah. Sorry, it's been
There-
so long. I don't go in and look at the acronyms so much anymore.
Oh, no,
there's
it's
so
all
much.
good. I was just curious at the time, but I really enjoyed this presentation.
Oh, thank you.
And PSIP's interesting because sometimes it seems like the least important thing in your signal and the most important, right? The part PSIP, we think of it as that's how that guide data gets there, right? The guide table. And that's nice to have. But if you grew up before this stuff, right, you just flipped channels. You didn't see a program coming up unless you had a fancy service. But PSIP also has that big top structure, the PAT and PMT. Without it, you can't decode any of it, right? So, you know, part of PSIP's kind of low priority and part of it is super critical.
Yep, that's 100%. And generally, when we start seeing overrates, and to kind of back up what Bill's saying here, generally when we see overrates, the encoders actually will start dumping PSIP data before anything else in the stream, because it has the highest potential that the stream won't fall apart because of it, right? The PAT and the PMT you cannot lose. If you lose those, the stream goes away. So it prioritizes what to dump first, and you could be missing your guide data, but your stream could still be on the air. So it's yep, they do prioritize it for sure.
Hey, Raymond shared a nice link for MPEG 101 is just continuing education. That is in the chat if anyone is interested. Thanks for that, Raymond.
That's a fantastic idea. I will take that. How about Josh Griffin? I'm going to call out Josh Griffin. He's one of my engineers. He's newer to this. He's been working on installing our new harmonic encoders. Josh, do you have any questions since we're just throwing all this at you?
Not really. I mean, pretty self-standard, pretty much.
All right, good deal.
I don't know how much time we had left, but I mean, I'm more than happy to go through anything else you guys are curious about.
Hey, this was great, especially after you explained the very basic fundamentals and you really ramped up. Very informative, and you filled in some blanks for people. We really do appreciate it. And Maybe one day we can talk about ATSC 3.0 if you're up for it.
Yeah, I'll be honest with you. There's a much better person here to talk to about that. His name is Mike Schmidt. He's been with, working on and part of the ATSC 3 ramp up for Heartland since the beginning. He works with all the vendors. He's been giving SPE and NAB presentations for years now. He's kind of, as I understand it, one of the experts.
Oh yeah,
I
he's
guess.
like a celebrity when we walk into the ATSC 3 meeting.
Yeah.
He's done like well over half the lighthouses and involved in every market.